actually 45 minutes. It'll be very fascinating presentation. If it isn't, I'm not going to get ready. Technology, they throw me down.
You ready? Let me have your attention, please. Let's begin. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker, who is a friend and colleague. It's Dr. Denis Beller. He's a research professor and race project director at the University of Nevada at Las Vegas. He also has an adjunct appointment at Idaho State University. Denis received a B.S. in chemical engineering from the University of Colorado in 1976, and then an M.S. in nuclear engineering from the Air Force Institute of Technology in 1981. And then he continued his graduate studies at Purdue University, receiving a Ph.D. in nuclear engineering in 1986. After that final degree, he joined the faculty at AFIT, and he was on the faculty for 8 years. Subsequent to his tenure at AFIT, he spent 5 years at Los Alamos National Laboratory, and he's been at the University of Nevada, Las Vegas for the past 4 years. Denis and I have been friends for a long time, and here lately we've been practicing reciprocity on making presentations at each other's respective universities. Last week I gave a presentation at UNLV, and so this week Denis is giving a presentation at our university. The title of his presentation is the Reactor-Accelerator Coupling Experiments Project, a la the RACE project, of the U.S. Advanced Fuel Cycle Initiative. Ladies and gentlemen, please welcome Dr. Denis Beller.
Thank you, Lee. As Professor Dodd said, the project that I'm going to talk about today is the Reactor-Accelerator Coupling Experiments Project, and this is a project to do experiments to investigate the coupling of subcritical nuclear assemblies and neutron-producing accelerators. If I can make this thing work real well here. The purpose of this project is to solve a problem. Okay, we're all engineers, or I'm an engineer, and I suspect most of the people here are engineers, and what engineers do is solve problems. The problem we're addressing here is what to do with used nuclear fuel. We have in the United States about 100 reactors, back-of-the-envelope kinds of calculations. These are the kinds of things you always should do before you use the computer, so that when the computer tells you something, you know it's right. Or you have an idea that it may be close to right. We have those 100 reactors produce about 1,000 megawatts of electric. Each reactor has 1,000 megawatts of capacity, so we have about 100 times that. And today we're operating at about 90% capacity factor. If we use an average efficiency of 33% and an average, what some people call burn up, I don't like that term, but other people do. 45,000 megawatt thermal days per metric ton initial heavy metal. That's the energy yield of the materials that we're using today. The combination of those things gives us about 22 metric tons of waste per reactor per year. With about 100 reactors, that means we have about 2,200 tons of waste. We have a little bit more than 50,000 tons in inventory today, and a little bit of mathematics and integration tells us that by 2010, which is the year the Yucca Mountain Project, our high-level waste repository, was supposed to open, we would have more than 70,000 tons of nuclear waste. That is, in fact, the statutory capacity of Yucca Mountain. We will exceed that capacity now because the DOE has told us that the project will not open until at least 2012. I suspect that'll be delayed again. We're going to exceed the statutory capacity of our waste repository before we even open it for starting to use store nuclear waste. Now, we've been studying this problem for a long time. When I worked at Los Alamos, I actually joined the tail end of a project that we called the Accelerator Transmutation of Waste Project, where Los Alamos was looking at using accelerators to get rid of nuclear waste. This project, at that time, we did some studies. We got a congressional earmark to do a systems analysis to see what it would take to actually do this job. This Los Alamos project, where they spent about $10 million in the first 10 years of Los Alamos's money, which was they got, of course, from the DOE, became a DOE project in 1999. And that year we did a roadmap for Congress. We wrote a report that we submitted to the United States Congress that explained how we would go about doing this, how long it would take, how much money it would take to develop the technology, and then how much we projected it would cost to actually destroy the waste over a period of about 100 years total. The number that we used in that report was 87,000 tons that the U.S. nuclear fuel industry would ever generate in its entire lifetime, okay, which was already in excess of the statutory limit, but not much in excess. We did systems modeling, of course, to produce that number and to figure out what we were going to do. And, of course, when you do systems modeling, engineering studies, you do a lot of approximations. The scenario that we used in that study in 1999 was partly because of decisions we made, but mostly because of decisions other people made. When you do a project for the government, you can't make other government organizations look bad, so you've got to follow what other people say. So we had to go by the Department of Energy's Energy Information Administration and Department of Energy's radioactive waste offices. We had to go by things that they had already come to conclusions about, and one of those was we would never have any increase in productivity from the existing reactors. We had no license extensions. At that time, there were no license extensions in the nuclear industry. The Energy Information Administration was predicting that a large number of our nuclear reactors would actually shut down before they had generated 40 years of electricity. And we also were never going to start up any reactors that weren't operating at that time in 1999. We would not build new plants. And, of course, there was no such thing as recycling in light water reactors. We couldn't even discuss it. Well, as you know, if you pay attention to anything about the nuclear power industry, we've had a lot of changes since then. About a third of our plants now have 20-year license extensions, and the reason that says beyond is because I went to Washington a couple of weeks ago, and I was told that the nuclear power industry is actually making purchases today for another 20 years beyond that. So they're making their decisions, they're planning and purchasing equipment that will last for a total lifetime of 80 years for nuclear power plants. So we're going to have power plants running a lot longer than we thought. We also have increased capacity, which means we're generating increased amounts of waste because we've been upgrading our power plants and uprating the power plants. So we're upgrading them by adding new equipment and uprating them by doing better numerical studies and convincing the Nuclear Regulatory Commission that you can make more power than you thought you could. That you can make more thermal power. So we're making more thermal power and we're making more electricity out of that thermal power. Both of those things give us additional waste. We have increased productivity today. We have over 90% capacity factor. The capacity factor was in the mid-80s in 1999 when we first did that HEW study. Increased capacity factor means you generate more waste per day. The result of that is that we're going to have a lot more waste from these nuclear plants than that 70,000 that will fit in Yucca Mountain or that 87,000 that first number that we used in 1999. This is just 4 years later from that FY99 report. In addition, not only can we now talk about recycling used nuclear fuel in light water reactors, we're actually required by law to investigate. The Department of Energy budget says in the law that gives the DOE its budget that you will investigate recycling used nuclear fuel. So obviously, we made at that time what we considered to be good assumptions, or at least assumptions that we had to use. Now we've got a modernized industry that's doing a lot more, and instead of 70,000 tons of used nuclear fuel, we'll have, I forget to use this, we'll have something like 150,000 tons from our existing reactors by the 2050s. Use the green one? Okay. In addition, the Nuclear Energy Institute has published a report called NEI Vision 2020, where they say they intend to raise their capacity by 50% by 2020. The DOE has a Nuclear Power 2010 program. We're already planning to build a next-generation nuclear power plant at Idaho National Laboratory. So we're talking about it not just increasing nuclear waste production from what we have, but increasing the number of plants we have, which will also add to that. So if we look at the implications of that, now we're looking at 120,000 tons sometime in the 2020s. Okay, that's very soon. That's 15 years. That may seem like a long time to the students in here, but to me that's not a long time. And that 120,000 tons has a meaning that I'll show in a moment. Now we're starting to talk about nuclear power for other things. There's a town in Alaska that's looking at putting a nuclear battery in because it costs them 40 cents a kilowatt hour to generate electricity because they have to barge oil up a river when it's not frozen for 1 month during the summer. We have hydrogen production that many people are promoting the use of nuclear power to generate hydrogen for desalination, like we did after the tsunami off of Sri Lanka. I don't know how many of you saw the nuclear power desalination plant over there where they were generating fresh water. I'll bet every one of you saw it if you watched the news, but you didn't hear about it. It was called an aircraft carrier. They were using the nuclear power plants on the aircraft carrier to make fresh water. And we also have industrial heat. Well, when you add all those things together, we're talking about 120,000 tons in 20 years and 200,000 tons before the 2050s. Okay, 3 times the capacity of Yucca Mountain. So what's the impact on repository licensing? Well, this is a graph that the Department of Energy produced, and you can see the production rate. This is a flat slope. Amount divided by time gives you the slope, which is a rate. Okay, the rate here is constant. They're saying that there will never be, through the year 2050, an increase in the production rate of waste. Well, we know today that's wrong. This graph was produced a couple of years ago. As a matter of fact, it isn't just wrong for the future. That graph is wrong for the present. The real graph looks something like this, and actually I did this graph about 1.5 years or 2 years ago, and it's out of date already because in a recent report I saw by one of the systems modelers for the Advanced Fuel Cycle Initiative, that date has changed to 2010. We're actually projected now to exceed the capacity of Yucca Mountain in 2010. This date, let me use black on this one, this date here has changed to about 2020, and there's that 120,000 number you see. This is the physical capacity of the Yucca Mountain project. Okay, the statutory capacity is 70,000 tons, but it actually just requires a change in law to increase that capacity. Well, it's a lot of money, too. I mean, you're going to have to dig bigger holes, more tunnels. But we can go to that capacity. But when we exceed that amount of used nuclear fuel, we've got to open a second repository. And living in Nevada and seeing the resistance of the public to the current repository, I don't believe that's going to happen. But what's really telling about this graph is the slope. Look at the slope on this, where it could approach here. Okay? That says we're going to need to open a new repository every few years if nuclear power truly expands to give us hydrogen, more electricity, desalination, thermal energy, etc. We're going to need a new repository in the United States every few years because that slope is just going to keep increasing. Well, there are a couple of options of disposal for this high-level waste. The first of those, of course, is what's called the once-through fuel cycle, which is not really a cycle. It's basically burying used nuclear fuel, and this is the option that's preferred by the National Academy of Sciences and by the nuclear power industry. It's preferred by the nuclear power industry because they believe it's the fastest way to get used nuclear fuel off of their sites, which is what they need to do so they can keep generating electricity and keep making a lot of money. However, by definition, the once-through fuel cycle is not economical. And I'll let you look up the definition of economical so you can decide for yourself whether that's true or not. Direct disposal faces many challenges. Of course, you probably see if you read the papers and look at it at nuclear news and watch TV that there's some political opposition to direct disposal of used nuclear fuel. That political opposition obviously is strongest in Las Vegas, Nevada. There's a public acceptance issue, not just in Las Vegas, but nationwide, and that public acceptance issue is actually fueled by the political opposition, and conversely, the public acceptance fuels the political opposition. The politicians don't really believe it's that dangerous, but their constituents won't vote, the majority of their constituents won't vote for them if they support a Yucca Mountain type project or any other kind of project like this in any state in the Union. It's simply going to be terribly difficult. We also, in addition to those policy issues, we have licensing and regulatory issues. Regulatory, who's going to watch this stuff with thousands of tons of plutonium in it for 10,000 to 100,000 years? And licensing issues, will the NRC really license the Yucca Mountain? I know a lot of people are not convinced that will actually happen. So those are issues that have to be addressed in the future. In addition, we have uncertainty for predicting what's going to happen in the world in 10,000 or 100,000 years from now. We have uncertainty in predicting what's going to happen with the materials that we use in the Yucca Mountain repository. Uncertainty with the condition of the earth, earthquakes, weather, for instance. Right now, there's no water in the Nevada desert where the Yucca Mountain project is. It is so dry that cactus will not grow there. They have rat droppings that are 50,000 years old in the ground at the Yucca Mountain waste site. Okay, 50,000 years old, and they're still rat droppings because there's no moisture there. It's absolutely, the water, they do get a couple of tenths of an inch of rainfall a year, and it falls on the ground, and it won't even soak in. It just runs off and evaporates. We have snowfall in Nevada that doesn't hit the ground. I've seen it. It never reaches the ground. It's so dry there, it evaporates before it reaches the ground. An option for these to take care of this problem is to recycle that used nuclear fuel and then to transmute a very small fraction of the waste that's in it. And I'll discuss how small that fraction is. That offers us potential solutions to this dilemma of what we're going to do with this growing amount of nuclear waste that we're creating from our commercial nuclear power plants. So what we want to do is create a technology where we can reduce the radiotoxicity and the volume of waste, reuse some of it, recycle the uranium, reuse the fissile materials for sure. The first thing you have to do that is take that used nuclear fuel and run it through a chemical process that allows you to make new uses of the material. We have developed both aqueous processes and pyrochemical processes, molten salt processes that work. We've demonstrated they work. Mixed oxide fueled, once you've done the separations, then you have to get it back into a reactor to get rid of the troublesome material. Okay, we've developed mixed oxide fueled light water reactors. The French are using those today. We don't use that in the United States, but we're preparing to. We're starting to prepare some plutonium, some weapons-grade plutonium fuel to put into United States reactors to demonstrate that we can destroy weapons plutonium by using that material up in reactors. So we will demonstrate that. We'll also look at high-temperature gas-cooled reactors as a way to get rid of the waste from nuclear power. We're also going to be using this technology in fast breeder reactors in the future. But we can use a fast reactor to get rid of troublesome actinides, higher actinides that won't fission in a light water reactor because they're non-fissile. They're fissionable but non-fissile. And finally, we have accelerator-driven subcritical systems, which is the part of this research program where I work. Most of the long-term hazards from used nuclear fuel are from just 1.1%. The majority of fuel is 95.6% uranium. Okay, it can be separated. We've demonstrated we can separate it cleanly. We've actually done that with real used nuclear fuel in the AFCI project. We separated 99.99%, recovered 99.99% of the uranium, and it was 99.999% pure. This material was so clean you could hold it in your hand safely. The uranium from real used nuclear fuel. About 3%, the next largest fraction, is stable or short-lived radioisotopes. Those can be separated, set aside, not in a repository. They can be put in a repository, but they don't have to be. You could set them aside, let them decay away, and in a few tens of years, they would be benign materials, non-toxic, non-radiotoxic. 0.3% is cesium and strontium. This is part of the problem of the Yucca Mountain project because those are two of the main isotopes that produce heat. Okay, those are what cause the heat management problem, and they can be separated. Chemically, it's pretty easy to separate them and recover them, and stored in a special form with special cooling so that they don't cause a problem. We might store them above ground for a while, and they also will decay away in a relatively short period of time. Then we have 0.9% of used nuclear fuel is plutonium. Okay, that means almost 1 out of every 100 tons of used nuclear fuel is plutonium. That's a tremendous quantity when we're talking about hundreds of thousands of tons of used nuclear fuel that will generate through the years. If we actually put that in a repository, we're talking about burying thousands of tons of plutonium. That today is really lousy stuff. But remember, the bad stuff is because it's decaying. In plutonium, the reason it's not good for making explosions from is because you've got isotopes of plutonium that are generating heat, Pu-238, which we use in our spacecraft, by the way, and Pu-240 and 242, and isotopes that are producing neutrons. Okay, well, those things are doing that because they're radioactive. So in 10,000 or 100,000 years, those isotopes will decay, and you'll end up with what probably could be considered a pretty good quality of plutonium. 0.1% of the used nuclear fuel is minor actinides: neptunium, americium, californium, etc. So those are sometimes a problem. They are also part of the heat generating problem and part of the long-term repository impact from the Yucca Mountain project. And finally, we have 0.1% that's iodine and technetium. But I think to use black up. So we have, there's a major problem, but that one can be recycled in light water reactors. We're not sure if we can recycle that in light water reactors, and we may need accelerator-driven transmutation systems to destroy those. It's going to take a lot of neutrons to do that job. The impact of doing that is that this is time. There's 10,000 years, and this is a graph of the relative ingested toxicity of used nuclear fuel versus time. Natural uranium ore falls on this straight line, and if we just bury the used nuclear fuel in 10,000 years, we're still above that line of natural uranium. If we only take the actinides out, the plutonium and the minor actinides out, we drop below that line in about 400 years. Okay, we may not know how to build facilities and containers that will last tens of thousands of years, but we do know how to build things that will last 100 years or 200 or 500 years. We've demonstrated that all over the world. We've got things like the Parthenon and churches and pyramids and other facilities that we've built that have actually lasted that long. We've got, as I said, rat mins in the desert that are 50,000 years old. So we know there's ways to do things like that. So if we can, now this is, you know, that one of those is the ideal case, and one of those is not doing anything. Reality will probably fall somewhere between there, but management time of less than 1,000 years. The impact of this technology, if we did this, was that we would never actually come above this line. That line may go out straight, but we actually can use AFCI technology and reduce the impact of used nuclear fuel. And in fact, if you look at the time scales of actually storing used nuclear fuel, we wouldn't, even if we start filling the Yucca Mountain repository in 2015, we're probably not going to have it full until out there. So we can actually start reducing the amount and may never actually need that second repository. So here are the goals of the Advanced Fuel Cycle Initiative project. First of all, we want to reduce the toxicity, the volume, and the heat load of the on the existing Yucca Mountain repository. That impacts the design, it impacts the operations, the future operations, and of course those two things mean it's going to impact the cost actually of operating a Yucca Mountain repository. Now part of that cost impact is going to have to be spent on the recycling operations, because recycling used nuclear fuel is not any more break even than recycling plastic jugs or newspapers. Okay, they cost money. Recycling things cost money. So you're going to have to pay for this. It's not a zero-sum game, almost certainly not a zero-sum game. Other nations have decided that it's worth the cost to do that. France, Japan, Russia, Great Britain, several other nations are recycling the used nuclear fuel. They're not breaking even either. They're not making a profit from doing that. Second thing we want to do is recover some of that energy value, because we know how important energy is to our nation and to the world. Energy saves lives. Okay, so we want to recover that energy value. Many of us believe, I believe, that throwing away this energy value is really truly a waste, and that's why it's not economical. We also want to reduce the inventories of plutonium that are available in civilian fuel cycle. And to do that, you're going to have to fission it. And finally, we want to eliminate the technical need for a second repository. To eliminate the technical need for a second repository, we have to start with the first ton of used nuclear fuel. Okay, we can't talk about disposing of most of what we've got today and starting with some future fuel cycle, some future equilibrium fuel cycle. We need to look at every amount of fuel that we have. Okay, so to impact this decision, we're going to have to do that. The Secretary of Energy is required by the federal waste law to recommend to the President of the United States between 2007 and 2010 whether or not the United States needs to build a second high-level waste nuclear repository. So that's the goal of our project, is to develop the technical justification for the Secretary to be able to tell the President we don't need to do that. Okay, we have to recycle in order to make that recommendation. I don't think any president is going to want to take the recommendation from the Secretary of Energy that it's time to start Yucca Mountain number 2, because it isn't going to be in Nevada. The reason the law was written the way it is so the second repository would be in another state, and those other states have all already said we don't want it. So I think this program is just going to naturally evolve. So what I want to talk about for just a few moments is something I mentioned at the start, the genesis of this program in the United States Department of Energy. As I said, we started out as a Los Alamos ATW Laboratory Directed Research and Development Project. We spent about $10 million over about 10 years. We started, first of all, doing a research project looking at molten salt reactors. We had a review at MIT in 1998, and then they changed directions to look at lead-bismuth-cooled accelerator-driven transmutation systems. And the lead-bismuth technology comes from the Russian nuclear military submarines. They have some of their submarines have lead-bismuth-cooled reactors in them. As I said, in 1999, Congress gave us some money to do an ATW roadmap. That roadmap was not just Los Alamos. There were a lot of national laboratories and a couple of universities involved in that project. They must have liked what we told them, because they gave us a little more money than the next year to actually begin a research and development program. Unfortunately, that was about a third of what we told them in the roadmap we were going to need to do the project, and that has been true every year since then. This technology is going to take billions of dollars to develop, and over a long period of time. And at $10 million a year, it's going to take a long time to accumulate billions of dollars of expenses. In 2001, the project was combined with another Department of Defense, or Department of Energy program called the Accelerator Production of Tritium Program. They decided to use the TVA reactors to make tritium instead of using an accelerator facility to generate neutrons for that. So the APT project was shutting down, and the two programs were combined. It became what was then known as the Advanced Accelerator Applications Project. That stayed that way for 2 years, and then it became the Advanced Fuel Cycle Initiative Project, and it has been that way now for 3 years. We are getting on the order of about $60 million a year, and the President has put into his budget for the first time $70 million for next fiscal year for the AFCI project. Well, what is transmutation? I keep mentioning this word, and not everybody is familiar with what transmutation is. I would be willing to bet that, as a matter of fact, that more people know the word in Las Vegas than know the word in Tennessee. They don't know what the word means, but they know transmutation exists, and it's an alternative to Yucca Mountain. The transmutation simply is a reaction that changes the contents of the nucleus. You can change the number of protons, the number of neutrons, or both. Natural decay is a transmutation reaction. We can also drive it. You can drive it with neutrons, you can drive it with protons, you can drive it with gamma rays, you can probably drive it with other small particles. We've known how to do this for a long time. The physics is relatively straightforward. We know the reactions that occur. We know the probabilities of occurrence. We know how to make the particles that make transmutation occur. You can, in fact, turn lead into gold. You just need a big source of neutrons and a lot bigger source of money, because the gold will never be worth what it actually costs you to make it. That's one of the issues, is because these processes are not very efficient, we have to figure out the methods. For this type of transmutation that we're talking about, we want to destroy actinides, the higher actinides, and destroy a couple of the forms of waste that I mentioned. So what we need is a neutron, either from fissioning this, or from an external source, or from a light water reactor, or from something that will then react with plutonium or minor actinides. Oops, I'm supposed to be circling these. Okay, so we start with a neutron, we react that with plutonium or minor actinides, we get fission products, and we get more neutrons. And if we do this job right, we get enough neutrons to continue that process. We get more fissions of more materials, plus we take a few of the neutrons to react with these problematic materials like technetium, and a couple of neutrons and a technetium turns it into ruthenium, a couple of neutrons and an iodine turns it into xenon. Both of those are non-toxic, non-radioactive elements. Of course, in the process, we're doing more fissioning in a nuclear reactor, so we're creating more waste. We're getting more fission products, more iodine, more technetium. We're going to have to do some recycling, but we'll end up in the end here with fission products and xenon and ruthenium. Okay. If we do the job really well, we'll have a high... The challenge then isn't, the physics looks pretty easy. The challenge is to do it effectively. And that means we've got to have nearly 100% conversion in our processes. We've got to have low processing losses in chemical process streams. You can't have a lot of the plutonium and other materials ending up in your waste, because then you're just going to create a bigger volume of waste that you're going to have to dispose of. You've got to be accident-free with lower proliferation risks, reduce waste toxicity and volume, and have an acceptable impact to the cost of the nuclear fuel cycle. Again, that doesn't mean a zero impact, but it's got to be acceptable to the government, to the public, and to the utilities that are going to have to do this. The transmutation strategy is then to partition the used nuclear fuel into a bunch of separate components, discard the uranium stable elements, or store the uranium for future use, form the transmutation fuels from long-lived radionuclides, and transmute those into short-lived or stable nuclides. And then at the end of that whole process, you'll have a smaller volume of waste that's less radioactive, and that has a shorter total lifetime for management. So there's a lot of big challenges. Now, one of a system or a combination of systems that we're using actually uses two different types of reactors, at least two different types of reactors. So the first thing you're going to notice is that with this fuel cycle, it's pretty straightforward. Okay, that's the one-screw fuel cycle. You put it in a reactor, you take the waste, you put it in a canister, and then you put it down in the repository. As you can see, the other process is much more complex, which means we're going to need a lot more people with jobs. That's your job. Separations, and you take that fuel up into a reactor fuel cycle. In this case, we're looking at here probably a light water fuel cycle, the same way the French are doing. So this is the LWR. Once you finish that process, though, you have mixed oxide fuel that comes out of that reactor. Nobody has ever recycled mixed oxide fuel. The French do not recycle mixed oxide fuel. They separate it, they store the plutonium for use in a fast reactor someday. They don't recycle it. So someday, the French are going to, they've done this part, now they've got to do that part in the future, and that's the part we're looking at right now, is the second series of reactors. You won't need as many of them, but they're going to be more complex systems. Back a second. One of the drawbacks of this technology, though, is this right here. We went from one waste stream to 9 waste streams. Okay? That's a management problem. It's an engineering problem. It's a challenge. We've got to make sure that those 9 waste streams are not bigger than the 1 waste stream, and we've got to make sure that they're kept from the public and they're safe and economical enough. The reason for looking at these fast systems is that they eliminate problems that you have with a light water reactor or critical systems. The subcritical operation of a facility at subcritical offers advantages. As a matter of fact, if you go so far subcritical, you're not even considered a nuclear facility. K-effective, criticality less than 0.95 can be considered non-nuclear. One of the advantages of this is that you can drive systems with low quantities of fissile material or high non-fissile burdens. Okay, fissionable materials, but not fissile, so it's difficult to keep a system critical. You can operate with fuel that can make a critical system unstable, okay, because you're not going to ever approach critical. Compensate for large uncertainties in reactor loading, or uncertainties in operation, or swings in reactivity. If you start off near critical and you go down farther subcritical, you're going to have less multiplication. Maybe you can have a system where you can turn the juice up to make no more external neutrons to keep that fissioning process going. And finally, what the good part of this is for academics is we've got a lot of research to do to develop this technology. But we're not doing this research by ourselves. We're actually partnering with many other organizations. We're actually building fuel in the United States to ship to France to expose in the Phoenix reactor in France, in the fast reactor in France. We're working with Russia, we're working with Japan, we're working with China, we're working with Korea, many European nations, all involved in developing this technology that in Europe they call partitioning and transmutation. Some in America call it reprocessing. I don't call it reprocessing because it's really not the same physical process as the reprocessing, which was designed to separate plutonium for making nuclear weapons. So there are several research areas. One of the first, of course, is separations and waste forms. That technology is led by Argonne National Laboratory. Second technology is subcritical transmuters. A technology that I won't mention that's not on these view graphs from here on is the use in light water reactors. That, of course, is another technology, creating those fuel forms. We are doing a lot of fuel form research that's led by Argonne and Idaho National Laboratory. Actually, the national technical leader is now at Idaho National Laboratory. For the accelerator-driven transmutation process, we've got the subcritical systems, the reactor part of it that needs design work, and then you've got the accelerator, which is a monstrously large, expensive facility that will be connected to an accelerator. And the part of my research project is the connecting of the two. Okay, we're not designing the reactors, we're not designing accelerators, we're using existing facilities and looking at the coupling of the accelerator generating neutron source and the subcritical reactors. And we're doing this in a project that we call the Reactor-Accelerator Coupling Experiments Project, where we're using accelerator-driven subcritical systems to actually conduct experiments in the United States. We're starting out small. We've already started out small, as a matter of fact. We're going to larger sizes, larger powers, larger accelerator powers, and larger reactor powers. We started out at the Idaho Accelerator Center at Idaho State University. We will soon have a subcritical assembly that's got a K effective of about 0.94. We're waiting for an NRC license to move that transportable nuclear reactor up to the Idaho Accelerator Center. I'll show a picture of it in a moment. We're also preparing to do experiments by coupling accelerators to the trigger reactors at University of Texas at Austin and at Texas A&M. This is a multi-year, 5-university program that very shortly will probably have a major international component as well when the Eurotrans group in the European Union joins our project. Lots of student research opportunities. We have lots of money to support graduate students. We have lots of undergraduate students. The reason we're doing this is because we want to demonstrate in the United States that we have the capabilities using our computer codes and our skills to design, model, and conduct these experiments. We want to predict and measure the subcriticality level, which is not an easy thing to do. You can do that if you start at critical. If you've got a reactor that can never be close to critical, this is the hard thing to do. Measuring how far subcritical you truly are is very difficult. And we want to measure subcritical multiplication both with the source on, which would be your normal operating mode, and which is the source off, which would be an accident condition, or could be an accident condition, or a failure condition. And we want to be able to predict and analyze subcritical source-driven transients. This is a big problem. This is a big problem. This is data from many years ago that is being repeated in Europe today. We are seeing the same kinds of things. The noise that you see in these signals is not the issue. These are measurements of the subcriticality level of a nuclear reactor in Germany. The issue is these were all made at the same time on the same reactor. And the subcritical reactivity, the reactivity of that reactor, varies by a factor of 2. The place that you make the measurement modifies the value that you get for subcritical level. Dr. John Lee, who was the director of the Michigan, or the head of the Michigan Nuclear Engineering Department, and his students applied a method called space-time correction to the prompt kinetics solution of the flux equation, and corrected these values, and you can see by doing that correction that you got the same value of criticality for all four of those different measurements, which were done in different places in the reactor. However, that took a week of calculations to do. And if you're operating a facility that's making 1,000 megawatts of electricity, you don't have a week to do a calculation that's going to tell you what's happening to your reactor right now. So we've got to develop numerical methods that will do this. The problem is the prompt kinetics equation doesn't work for source-driven systems. It doesn't work for two reasons. One, the flux shape is time dependent. PKE says you can separate the spatial dependence from the time dependence of the flux, the value of the flux, the description of the flux in a reactor. Okay, the flux shape actually changes in time. Not only that, because the neutron source is not the same for the accelerator source as it is for a fission source, your time dependence actually changes in time. The neutron lifetime of all of the neutrons in the reactor, when you turn an accelerator off, that neutron lifetime actually changes in time, so that the neutron decay constant that you use in the prompt kinetic equations, the alpha, e to the minus alpha t, alpha value actually changes in time. So you've got two issues there that are causing the PKE not to work. So what we're going to do with the RACE project is create steady state and transient benchmark measurements that people can develop new codes to, and we can confirm those new codes using these measurements. We'll test new computational codes and methods. We're going to spend a lot of time and a lot of money with students, and we're going to maybe even transmute some higher actinides during this process so that we can produce some good publicity for the federal energy program. This is a graph of the evolution of these accelerator-driven subcritical systems experiments with over time and with neutron source strength. The experiments that have been recently completed at Cadarache in France and at the CEA were with a DD neutron source. I've got to remember the circle things. DD neutron source of about 10 to the 8th neutrons per second and a DT neutron source of about 10 to the 10th neutrons per second. Currently, experiments are being done at Casaccia in Italy, with called Trade 1B, where they're using a DT neutron source of about 10 to the 9th, 2 times 10 to the 9th neutrons per second. The accelerator source for the electron LINAC that I'll show a picture of in a few minutes is about 10 to the 12th neutrons per second, and we can go up to possibly 10 to the 14th with small transportable electron LINACs, which may mean we can get up into maybe the upper tens to maybe 100 kilowatts of thermal power in a trigger reactor. At these levels, actually at about 10 kilowatts, you can start pretty easily measuring thermal feedback effects in these kinds of experiments. So we should be able to measure the reactor dynamics of an accelerator-driven system in the Texas A&M and University of Texas experiments using their trigger reactors. We were supposed to do this project in Europe with the trade. They were going to build an accelerator at Casaccia, which is the Italian energy and nuclear agency, research agency. Unfortunately, that project may not go forward. So the people who are actually working on that project now will probably join the RACE project and will bring their instruments, which are very highly developed, and bring their people to the United States and conduct experiments with our project. This XADS, way up here on the right side of this graph, would be an experimental prototype type of a system, and that would actually be a lower neutron flux than you would need for a production nuclear reactor where you would be generating electricity and destroying transuranics at the same time. I'm going to skip a couple of these. They'll be on the geograph presentation. The Muse DT source was, as I said, about 10 to the 10th neutrons per second. The trade proton source was supposed to be about 10 to the 15th. That's a pretty large jump in technology. The RACE project would fill that gap up and would give us learning along the way towards that trade project if, in fact, it does become reality. we can make about, as I said, about 10 to the 12th per second, and a neutron energy is between 1 and 25 million electron volts. For a high-energy accelerator transmutation of waste system that has a big proton accelerator, you would have neutron energies all the way up to the proton energies, which would probably be between 800 and 1,000 million electron volts, or a GeV, or maybe even higher. These electron linacs are really nice little systems. They're small. I mean, you know, like this. The electron linacs are second only to protons for generating neutrons per unit of beam power that you produce. They're not very expensive, and they're transportable. So they allow us to do academic experiments using the accelerators. We've done a lot of research. In this project, we're going to also have a variety of reactors. Unlike the European experiments where you had one reactor and one target located in the center, we can move our targets around. We can use 4 different types of reactors, different kinds of fuels, different kinds of reflectors. So we can create a set of benchmarks that we can make sure that codes that we develop aren't dependent on that one experiment that we did. You know, we don't want to develop a code that works for one specific experiment but doesn't work for over a large range. What we've already done so far is we've done static and transient analyses at the University of Michigan. We've done some benchmark studies for the NRC to validate our codes to make sure that when we told them we were going to have a K effective of 0.94, we weren't really going to have 1.02. We used MCNPX and MCNP for that. We have our license amendment application has been reviewed by the NRC. We received a response. It took us about a little over a month to reply to that response. We got that back into them, and so we expect a license within the next few weeks. We've completed design studies at Texas A&M for the Texas trigger experiments. Go back. There we go. We're developing instrumentation, and we've actually done experiments. This is part of the team that's working on this. Right now, University of Michigan, we will have a new student working there. Victoria Kulik got her Ph.D. Doing these kinds of studies, not just the studies for the race project, but also for the music experiment in France. And we've got faculty and students at Idaho State and Texas and UNLV. And yes, there is a relation. The accelerator and the large vessel, this is our subcritical accelerator-driven assembly at Idaho State University. The whole thing. That's it. This is the accelerator. This is there's a beam port right here, a vacuum port that goes inside this tank. And this tank contains the subcritical assembly, water moderator, and a graphite reactor. That's the whole thing. It's about 1 meter by 1 meter by 1 meter, the tank itself. And the accelerator is a little over 1 meter long. This is a target that generates the neutrons. Okay, what happens is the accelerator beam comes down a vacuum tube that's actually welded onto this flange. This is the flange that's welded to a copper and tungsten target and hits basically right there in an area about that big. It's a couple of millimeters across the electron beam. So all of the neutrons, the electrons in 25 million electron volt electrons are stopped almost instantly in that target. They produce high energy photons up to 25 MeV gamma rays. Those gamma rays then react with the tungsten and produce photoneutrons. And typically those photoneutrons will have a fission spectrum. It'll look just like a fission spectrum with a real small high energy tail. Okay, you've got maybe a few percent of your neutrons are up to the energy of the electron beam. And as I said, those are all produced right it's almost a point source. For calculations, this makes calculations pretty easy, and they're almost isotropic. The photoneutron production process at those energies is almost isotropic. So basically, you've got a point source of isotropic neutrons in the center of your nuclear reactor that you can do experiments with. One of the problems we have with this is that efficiency is very low. We get about 1 neutron for every 10 to the 3rd electrons, but we get 1 photon for every electron, at least 1 photon for every electron. So there's a large gamma ray flash in conjunction with the generation of the neutrons. And that gamma ray flash occurs while we're trying to measure neutron flux. That's a big technical problem. This is a picture of the target being tested for thermal performance. The reactor itself uses 150 uranium aluminum fuel plates. Zip through this, I'm running out of time. This is a picture of the actual assembly from the top. What we've done is we've created these trays, these modular trays that we can slide these fuel plates into, and we just stack 6 of those trays in a almost a circular cross-section, a little bit oval-shaped. This is a picture of it from a front cutaway view of how those would be stacked, of how the trays would be stacked. This is what it looks like from the top, with the target centered in the center of the assembly. Again, from the front, with all of the graphite reflectors and water moderator in place. We don't actually fill the tank all the way to the top with water because it really doesn't matter. Anything outside of that graphite doesn't communicate with the center of the fuel. This is that last picture is actually where we would have the fuel placed for the first experiments that we've already done. We can use 10 of the plates without the reactor license from the NRC. Unfortunately, we can't take all 150 up there, so we've only done plates. We've only done experiments with 10 plates, which is a K effective of about 0.2. Not close. We've done a lot of gold foil measurements, and this is a picture of a comparison between a MC&PX calculation and a gold foil flux measurement. And you can see that the two agree pretty well, normalized to each other. They agree pretty well within the errors of the measurements and the MC&P calculations. So we've got a pretty good handle on modeling the experiment, on creating it, on conducting the the time-integrated measurements. The time-dependent measurements are another matter. As you can see, we haven't figured that out yet. We're developing detectors right now. The gamma ray flash and the electromagnetic noise from this huge current power that we have to provide for the accelerator are both problems. So we're working on those issues, trying to develop the time-dependent measurements, because that's what you really have to look at. You need to look at the die away of the delayed neutrons immediately after they're produced. So immediately after that gamma ray flash and neutron flash, it's when we need to look at that slope. And the recovery time of the detector then becomes critical, in addition to shielding out all the noise from all of the electronics. This is a tentative schedule. We'll start experiments at University of Texas at Austin this summer. We're building the accelerator right now to take down there. We'll begin building the target very shortly. Their target won't be tungsten, a solid slug of tungsten that's 3.5 inches long. We'll probably have a target that actually contains uranium. Using uranium in the target so that you get photoneutrons and photofission from the uranium approximately doubles the neutron production. So we get a lot higher neutron yield and a lot higher power that way. We can go from a 5 kilowatt experiment, 5 kilowatts of fission power, to 10 kilowatts of fission power by replacing the target. We'll start experiments at Texas A&M in 2006, and we'll do 2 different reactors at Texas A&M. They actually have 2 different fuel loads there. Probably should wrap this up. In conclusion, the RACE project is a multi-university academic project. This is not a national laboratory project. This was created by Idaho State University, and it's being run by Idaho State University as an academic project. We expect to produce at least a dozen Ph.D. degrees and many master's degrees out of this research project, with students who are at UT, Texas A&M, at UNLV, at Michigan, and at Idaho State University. So needless to say, we have some funding, and I'm going to talk about that after this presentation is over. And students are doing the work. Okay, the faculty members are not running the experiments. We've got students and postdocs designing the experiments, doing the radiation transport modeling, doing the measurements, counting the counting foils, developing the detector systems, and executing the experiments. And in the future, they'll be analyzing those experiments and developing new numerical methods. Again, we're doing this so that we can demonstrate in the United States that we can predict and measure subcritical multiplication, that we can predict and measure source-driven transients, and that we can also map the source importance. By moving the target around, you can see how it couples, how a target not in the center of the reactor couples to the reactor. There are concepts where you might have one reactor with 10 accelerators, spread around it, each providing sources on the outside rather than in the center of the reactor, which is how our experiments will be. We're going to do this project now through 2007 and probably beyond. We have a few very strong congressional representatives who are providing the funding for these projects at UNLV, Idaho State, and next year probably at Texas as well. So this program will be ongoing for a long time. And as I said, we need graduate students. I need about 20 graduate students at UNLV for next year, and we need several at Idaho State University. And as I said, I'll discuss that more shortly. That concludes my presentation. I'd be glad to answer any questions. Probably should have wrapped up to give a little more time. Thank you.
Let's give him a round of applause. Okay, we have time for a few questions and comments. Yours.
You mentioned electron Linux for experiments, and you said that you produce 1 neutron per 1,000 of electrons. So that means 25 MeV, you spend for 1 neutron 25 GeV of energy. And I think in the final industrial scale of this idea, you will have to use the protons.
That's correct.
And what will be the parameters of the proton driver which will be needed for that?
The proton accelerators, we're probably going to need upward of maybe 1,000 MeV or GeV of energy per particle. And the reason you need that is because at that energy you get about 30 neutrons per proton. Okay, maybe 33 to 35 if you design the target just right. Neutrons per proton. So you get a high yield. Unfortunately, those accelerators are about a mile long. A lot of material, a lot of technology to be developed. You're probably going to have superconducting accelerator components. So there's a lot of technology. We know how to build these things, but today we don't know how to build them reliably.
Well, we are building one in Oak Ridge, which cost $1.5 billion.
Right.
It is about 1 kilometer long, and this is slightly one megawatt. And how much megawatt?
You're going to need about on the order of about 10 megawatts of beam power.
It will serve the needs of the whole nation, or it is just for one reactor?
For one facility.
For one, and how many facilities?
That's probably a few reactors, depending on what size thermal energy. You can look at the ATW report, and there's that. Remember when we did the ATW report, we were looking at destroying all of the actinides in fast accelerator-driven systems. Well, we figured out we needed about 60 or 70 reactors, accelerator-driven reactors, and each of those a facility would have 2 accelerators and 8 reactors. So you would take an accelerator and you would split its beams. So split its beam into multiple beams so that it would irradiate more than one reactor. We did that both because of the feasibility of sizes of things, as well as for increased reliability for the overall system. But you're right, these are big systems. But today we're not talking about doing that. We're talking about doing most of the transmutation in light water reactors, advanced gas-cooled reactors, advanced fast critical reactors, and then basically taking the tail end of that. The actinides will build up to non-fissile isotopes, and taking the tail end of that and putting them into accelerator-driven systems. So maybe a few of these to support 100 reactors in the United States.
Okay, I think we probably should continue the question and answer period downstairs at our reception. Let me make one final comment. I'm sure the students picked up on it. When he says UT, he means the University of Texas.
Oh, yes.
Okay. When we say UT, we mean the University of Tennessee. And it's clear what we mean when we say it, and it's clear. So at some point between Knoxville and Austin, there's a point of confusion. Right? People don't know what UT means. So with that comment, let's express our appreciation again to Dr. Beller for his presentation. And let me remind you that we do have a reception downstairs, and everyone is invited, and Dennis will be available to answer more questions. But let's give him another round. go.
Right?
Let me show you. I didn't.
Oh, I was sort of put it back.
But when they're both out,
Okay. Well, you told me that. I just